So first of all, integrating trig functions. There's a couple that you need to know off by heart, and that's the integrals of sine and cos. And then there's a bunch that will be given to you in the formula book. This is a copy of the EdXL formula book, but there'll be something similar in any of the other formula books as well. You'll notice that you're given some here under the integration section. Then you can also look in the differentiation section and work backwards. So for example, let's say we came across sec x tan x and we wanted to know how to integrate it. We could just work backwards and see that the integral would be sec x. You need to be careful with your constants and things like that, but the basic idea is there, given to you. Same with these ones. All the ones that you need to learn, hopefully you'll recognize these rules from differentiation as well, working backwards. But the integral of sine x is minus cos x, and the integral of cos x is just sine x. The rules for exponentials and reciprocals we need to learn. When you integrate e to the x, it just stays the same, e to the x. Same for when you differentiate it. And then the integral of 1 over x, or the reciprocal of x, is ln x. And x is inside the modulus symbol there. Now, in a previous video, I mentioned there's a trick for integrating functions when you have a linear function inside them. So I'm just going to write those general rules on the side here as well. So if we had e to the power of, let's say, ax plus b, where a and b could be numbers, when you integrate that, you keep the e to the ax plus b, but then you divide by the derivative of ax plus b, which would be 1 over a, because we're dividing by a. Similarly, if we had 1 over ax plus b that we wanted to integrate, we would do the ln ax plus b, because that's the general rule, and then we would divide by the derivative of ax plus b, so divide by a, same as doing 1 over a at the front. Now let's look at some examples. So example 1, find the integral of cosec 3x cot 3x dx. So this looks like one that could be in the formula book. So if we have a look there, we can see that if we work backwards from this information given in the differentiation section, if you want to integrate cosec cot, that becomes cosec. But again, we've got to be careful with any constants or negatives or anything like that. So the answer will involve cosec, and it will be cosec 3x in this case, because we've got cosec 3x cot 3x. But it's going to be a minus, and we need to put a 1/3 on the outside because we're doing an adjustment there for the 3x. We divide by the derivative of 3x, which is 3. And then we have to remember our plus c on the end. So once again, dividing by 3 or timesing by 1/3 because the derivative of 3x is 3. And it's a minus because there's a minus here that becomes a positive. So we have to flip the sign. Example 2, find the integral of cos squared x between the limits of 0 and pi over 2. Now this is a good example because in order to answer this, we actually have to use trig identities. In particular, the double angle formula for cos. So one of the versions of cos 2x is that it equals 2 cos squared x minus 1. And it's useful because if we rearrange to make cos squared x the subject, we can then use that in the integration. So if we rearrange to make cos squared x the subject, we're going to get this. And then we can put that inside the integral symbol instead of the cos squared x. The reason we need to do that is because we don't know how to integrate cos squared x straight away, but we do know how to integrate cos 2x. When we integrate cos 2x, we'll get sine 2x. And then we need to make our adjustments. So there's already a half on the outside, which would stay there. And then we're going to times by another half because that's us dividing by the derivative of 2x. So dividing by 2. We then have to integrate a half separately, which will become a half x. And then we're going to apply our limits. And before you do the limits, you might want to tidy up slightly. So a quarter sine 2x plus a half x with the limits, and then substitute the limits in. When you evaluate these brackets, you get pi over 4 for the first one and 0 for the second one. So overall, we're going to end up with pi over 4 for our final answer. Example 3, find the integral of e to the power of 3 minus x with respect to x. When we integrate e, it stays the same. So we'll have e to the power of 3 minus x still as part of the answer. But then we need to do our adjustment. So we're going to divide by minus 1 in this case, because minus 1 would be the derivative of 3 minus x, and then stick a plus c on the outside. Once again, got to do that adjustment for the minus x. Last example, find the integral of 2 over 3x plus 5 with the limits 1 and 2. Now for this one, because it's a reciprocal, we know that ln's going to be involved. So I'd probably go ahead and do 2 ln 3x plus 5 straight away, and then think about my adjustments. So in this case, I'm going to times it by 1/3 because 3 is the derivative of 3x plus 5. And we always have to divide by the derivative of what's inside the bracket, or in this case, the modulus. Limits are 1 and 2. I tidy up slightly before substituting in the limits. 2/3 ln 3x plus 5, and then sub in the limits carefully. Now, in a lot of exam questions, you'll be asked to give your answer as an exact answer. It means you want to leave it in terms of ln where you can. So I'd probably just do 2/3 ln 11 minus 2/3 ln 8. And then we could tidy this up pretty nicely because they both have 2/3 in the front. So we could combine that into 1 ln using log laws. 2/3 ln 11 over 8. Final answer. Unless, of course, they want it in another specific format, but you'll know that from the exam question. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.